Alright, now that you've seen the formal definition of finite automata, and we went over defining the first finite automata that we encountered in this class, let's take a look at a couple of other finite automata and start writing formal descriptions for these automata, and try to experiment and look at the kinds of languages that these automata recognize. After I go over a couple of these examples, then we see that we cannot really all the time rely on state diagrams or transition tables to define our automata, and so we would have to effectively rely on the description and the design of our transitional function delta to be able to define and work with a general form of these kinds of automata. And then I'll talk about formally defining computation, because at this point we should be able to formally define what computation means at this point, and then we look at how we can design automata. And that would conclude this unit of working with finite automata. So first, let's take a look at a couple of examples. Alright, so for this example, let's suppose that we have this automaton m sub 2. And I'm going to represent this with two states. The state q sub 1, which will be my initial state. And as we said, the initial state is represented in the state diagram by an arrow pointed to it. And its accept state is going to be q sub 2. It's going to have one accept state, just like the previous automata we saw. This automata will stay in state q sub 1 when the input symbol that is processing is 0. Then upon seeing a 1, it will transition to state q sub 2. In state q sub 2, if it sees a 0, it moves back to state q sub 1. And when it reads a 1, it will stay in q sub 2. So now we're going to formally define this automaton. Again, remember, a finite automaton, or in our case, the deterministic finite automata, is a 5-tuple. So m sub 2 is equal to a sequence of 5 elements, which we represent with letters enclosed in parentheses. Q sub 1, a finite set of state, sigma, a finite set of alphabet, delta, the transition function, q sub 0, we call it the initial state or the start state, and f being a finite set of states called accept state. So let's define these individual elements one by one. We'll start with element number 1, q. Q is a finite set of states. So it is, in my case, 2 states, a set of 2 states, q sub 1 and q sub 2. 2. Alphabet. Sigma is a finite set of alphabet symbols. In this case, it's 0 and 1. 3. Delta is a transition function over from the domain of q cross product with sigma. And let me just rewrite the sigma a little bit neater. Sigma cross product with q cross product with sigma over onto the range q. I'll define this a little bit later. Let's just take the initial state and the set of accept states out of the way. So q sub 0, the initial state, in my case, is going to be q sub 1, and the set of accept states f is going to be equal to a set of q sub 2. Again, I would like to emphasize the fact that q sub 0 is just q sub 1, not the set of q sub 1. And also f is the set q sub 2, not just q sub 2. So if you define these as these red ones, that's wrong. Q sub 0 is just one state. F is a set of states. In this case, the set happens to have just one state in it. So it doesn't necessarily is equal to q sub 2 is equal to set of q sub 2. Alright, next is going and defining the delta transition function. The easiest way to define your transition function is with a table. So delta, which is going to be from q cross sigma, 0 and 1 are the elements, q sub 1 and q sub 2 are the states. So the delta of q sub 1, 0, meaning that what does it do, what does the machine do if it's in q sub 1 and it sees a 0, it stays in q sub 1. When it is in q sub 1 and it sees a 1, it goes to q sub 2. If it is in q sub 2 and it sees a 0, it goes back to q sub 1. And when your machine is in q sub 1 and it reads 1, and is in q sub 2 and it reads 1, it stays in q sub 2. Now another way to show your delta functions is basically to enumerate and list it. So delta q sub 0 and 0, delta q sub 0 and 1, delta q sub 1 and 0. Actually, we'll call these q sub 1 and q sub 2, delta q sub 2 and 0 and 1. So delta of q sub 1 and 0, if you are in q sub 1 and see 0, you stay in q sub 1. If you are in q sub 1 and see 1, you go to q sub 2. If you are in q sub 2 and see 0, you go back to q sub 1. If you are in q sub 2 and you see a 1, you stay in q sub 2. So these two things are equivalent to each other. So you could either show your delta function as a table or list the delta functionalities as you see here. For all combinations of q sub i's from the set q, alphabet values 0, 1, 0, 1 onto q sub i's that are in set q. These two, and these are the representation of our functions. Remember that the formal definition is the whole definition of all these 5 tuples. So this whole thing is the formal definition. So this whole list is the formal definition, and the state diagram is basically an informal notation that kind of gets us to see the automata. Now, if you want to see and understand what this automata does, to be able to look at the languages that the language that it recognizes or the set of strings that it accepts, it helps us to just go over and try some examples as input and see what happens. When we experiment, we perform these experiments, we get to see how the machine works and its method of functioning becomes apparent after a few examples. So, for example, let's take a look at the machine on the input of 1, 0, 1, 1, and see what it does on this sample. So you start with q sub 1. When you see a 1, q sub 1 and a 1, you go to q sub 2. in Q sub 2 when you see a 0, you go back to Q sub 1, right? So if you're in Q sub 2 and you see a 0, you go back to Q sub 2. Then you are in Q sub 1 now, and you see a 1, you go to Q sub 2. And when you're in Q sub 2 and you see a 1, you stay in Q sub 2. At this point, you accept this string. Let's try another input. Let's do an input 0, 0, 1, 0, 1, 0. Okay, so we start in Q sub 1. When you see a 0, you stay in Q sub 1. You see a 0, you stay in Q sub 1. If you're in Q sub 1, you see a 0, you stay in Q sub 1. Or, according to the description of the delta functions here, if you are in Q sub 1 and you see a 0, you stay in Q sub 1. So you're in Q sub 1, you see a 0, you stay in Q sub 1. You're in Q sub 1 and you see a 1, you go to Q sub 2. From Q sub 2, if you see a 0, you go back to Q sub 1. In Q sub 1, when you see a 1, you go to Q sub 2. And in Q sub 2, when you see a 0, you go back to Q sub 1. Q sub 1 is not an accept state, so you reject this string. By going through examples of sample strings, we will realize that this machine accepts languages, this machine accepts strings that end with a 1. By looking at the state diagram, we can see that if the last symbol seen is a 1, or the last symbol processed is a 1, you are in Q sub 1, meaning that you were either in Q sub 1 and you processed a 1 and you ended up in an accept state, or you were already in Q sub 2 and you saw a 1, so you stay in Q sub 1. By looking at your transition table here also, you would realize that Q sub 2 here, these are your final states, which means that if you are in Q sub 1 or in Q sub 2 and you read a 1, you go into Q sub 2 or you stay into Q sub 2, which is an accept state. In contrast, if the last symbol processed is not a 1, basically it's a 0, meaning that if you were in Q sub 1 and you saw a 0, or if you were in Q sub 2 and you saw a 0, you go back to a state that is not an accept state, which means that that string is not going to be accepted. So by this, we will notice that the language of this machine, the language of M sub 2 here, is the set of all strings that end with a 1. Okay, or in other words, L of M sub 2 is going to be language A, where A is the set of all W's such that W ends in 1. All other strings will be rejected or not accepted, except for the strings whose last symbol is a 1. So this is one example of a finite automaton. Alright, let's take a look at another example of finite automata. Again, we'll have a finite automata with 2 states. Actually, this time we're going to have Q sub 1 to be both the start state and the accept state. So again, in Q sub 1, with a 0, we stay in Q sub 1. With a 1, we go to Q sub 2. In Q sub 2, with a 1, we stay in Q sub 2. And with a 0, we go back to Q sub 1. again. So this is M sub 3. Formally, we'll define M sub 3 as a 5 tuple Q, comma, sigma, comma, delta, comma, Q sub 0, comma, F, where Q is a finite set of states, which is going to be Q sub 1, comma, Q sub 2. Sigma is a finite set of alphabets, symbols, which is going to be 0 and 1, 3. Delta is going to be a transition function from Q cross sigma onto Q. And we'll get back to defining delta a little bit later. Q sub 0, our start state, is going to be Q sub 1. And 5, the F set of accept states is going to be a set composed of Q sub 1. This is a finite formal definition of the M sub 3 that we have here. Notice that practically the only change is the fact that now the set of accept states is the set Q sub 1 instead of set Q sub 2, which was our previous example. So the delta, my transition function, again is going to be a table. I'm going to represent it in a tabular format again, of Q cross sigma. So Q sub 1 and Q sub 2 are my states on this transition table, and 0 and 1 are going to be my inputs. Over Q sub 1 with a 0, we stay in Q sub 1. Being in Q sub 1, seeing a 1, we're going to go to Q sub 2. If we are in Q sub 2, we see a 0, we go to Q sub 1. And if we are in Q sub 2 and we see a 1, we stay in Q sub 2. Now this time, the accept states are Q sub 1s. Alternatively, we can represent our delta with just enumerating the transition values. So delta over being in Q sub 1, seeing a 0, delta being in Q sub 1, seeing a 1, delta being in Q sub 2, seeing a 0, and delta being in Q sub 2, processing a 1. So according to this transition tables as well as the transition diagram, this is going to be a Q sub 1, this is going to be a Q sub 2, this is going to be a Q sub 1, and this is going to be a Q sub 2. And again, our accept states are Q sub 1. Now if we want to look and see the processing of this machine and what kind of languages it accepts, and of course looking at the previous example, that one, M sub 2, recognized the language of all the strings that ended with a 1, because all of these arrows with label 1 ended in Q sub 2, and Q sub 2 was an accept state. In this example, all of the arrows that have 0 as labels, they end up into Q sub 1, and the Q sub 1 is an accept state. So we would immediately see that this language accepts any string that ends with a 0. Let's take a look at a couple of examples. So let's say that our input is this string 0, 0, 1, 1, 0, 1, 0. Okay, so we start in Q sub 1. When we see a 0, we stay in Q sub 1. We are in Q sub 1. When we see a 0, we stay in Q sub 1. We see a 1, we go to Q sub 2. We see a 1, we stay in Q sub 2. We see a 0, we go back to Q sub 1. We see a 1, we go to Q sub 2. And we see a 0, we go back to Q sub 1. It is an accept state, so that string is accepted. Let's try this string. 0, 1, 0, 1, 1. So we start with Q sub 1. You see a 0, stay in Q sub 1. You see a 1, go to Q sub 2. See a 0, back to Q sub 1. See a 1, go to Q sub 2. See a 1, you stay in Q sub 2. and that is rejected because you did not end up in an accept state. Let's start an input that starts with a 1, 1, 0, 1, 0, right? So you start at q sub 1, see a 1, go to q sub 2, see a 0, back to q sub 1, see a 1, go to q sub 2, see a 0, go back to q sub 1. Q sub 1 is an accept state, so you accept that string. So you see all of these strings that end with a 0, they'll be accepted, and the strings that end with a 1, they end up being rejected. Now, there's a interesting question, and that is what if our input doesn't have any strings in it or any symbols in it? What if our input is nothing, right? So this is a very interesting question. Notice that when your machine starts, before it starts processing any input, it starts in q sub 1, and q sub 1 is an accept state, which means that even if your string is empty, it is accepted by the machine, because the machine starts and then ends in the accept string, in the accept state q sub 1. And since the input didn't have any element in it, the machine didn't go to any other state. So it stayed in its own accept state, which was the start state as well. So we usually denote the input, the empty string, or the empty symbol, with a small epsilon, which means that the symbol epsilon will be accepted, and epsilon is effectively the empty string in our case. So the empty string is also accepted. So what is the language of m sub 3? So the language of m sub 3 is a set A, where A is any string W such that W is the empty string, or W ends with a 0. So if W is the empty string, or W ends in 0, then this language, this string will be accepted. So A in this case, in the case of m sub 3, the language of m sub 3 is the set of all strings that either end in a 0 or they're empty. And the reason that our language accepted the empty string was because the input state was one of the accept states. Remember, accept states is a set of states that the machine accepts, and if that set contains the start state, then your machine recognizes the empty string. Alright, now we'll take a look at a 5-state machine, m sub 4, which is a little bit more interesting in terms of what it does. So this machine basically has 5 states. So we start in state S. So we start in state S. This is the state that has an arrow pointed to it. Out of nowhere, and then it goes to the left set of states if it sees the input symbol A, and over the input symbol B, it goes to the right set of states. So if it sees A, it goes to q sub 1, and if it sees B, if the first element on the string is B, then it goes to the right hand states. So denote them as R sub 1. And then upon seeing A in q sub 1, you stay in q sub 1. If you see a B, you go to Q sub 2. In Q sub 2, if you see a B, you stay in Q sub 2. And when you see an A, you go back to Q sub A, Q sub 1. In the R sub 1, if you see a B, you stay in R sub 1. If you see an A, you go to R sub 2. In R sub 2, if you see an A, you stay there. And if you see a B, you move back to R sub 1. So this is a 5-state machine. You call it, in this case, M sub 4. And that's the state diagram for it. Now let's formally define this M sub 4 and see what it does, and then try to find out the language that it accepts, or the set of strings that it recognizes and it accepts. So again, M sub 4 is a 5-tuple: Q, sigma, delta, Q sub 0, and F. And then we're going to have to formally define every single one of these 5 elements. So 1, Q. Q is a finite set of states. Now in this example, Q is the set made of S, Q sub 1, Q sub 2, R sub 1, R sub 2. So S, comma, Q sub 1, comma, Q sub 2, comma, R sub 1, comma, R sub 2. Now notice that Q is a set, so I could alternatively also just represent it. But it's basically the same thing if I also represent it like this: S, R sub 1, Q sub 1, R sub 2, Q sub 2. This is practically exactly the same thing. Remember, in sets, order doesn't matter. So I'm going to basically just put a footnote here saying that in sets, order doesn't matter. Okay. So the set of Q is just a finite set of states that I have. Second element I need to define is the alphabet, sigma, which is a finite state. And in this example, sigma is made of symbols A and B. Remember, in the previous examples, the alphabet was 0, 1. In this example, the alphabet is A and B. 3. Delta is a transition function, which is going to be over Q cross sigma onto Q. The Q sub 0, my initial state is equal to S. And the set of accept states is a set. In this case, I have 2 accept states. So it's going to be Q sub 1, comma, R sub 1. Again, remember, order doesn't matter. It's the same as saying R sub 1, comma, Q sub 1. This is the set of accept states. So now I need to go ahead and formulate my transition table. Now notice here my transition table is going to be much larger because I have 5 input states and 2 symbols in the alphabet. So effectively the cross product of a 5-element set by a 2-element set is going to be a 10-element set. So my transition table is going to have 10 entries in it. So I'm going to define this again here. So it's going to be a table from Q cross sigma, right? So S, Q sub 1, Q sub 2, R sub 1, R sub 2, and the symbols are going to be A and B. So this is going to be my delta transition function. Now in state S, when I see an A, I go to Q states. When I see a B, I go to R states. So if I see an A, I go to Q sub 1. If I see a B, I go to R sub 1. So Q sub 1 and R sub 1. Then in Q sub 1, when I see an A, I stay in Q sub 1. With a B, I go to Q sub 2. So I'm going to stay in Q sub 1. If I see an A and I'm in Q1, if I'm in Q1 and I see a B, I go to Q2. In Q2, when I see an A, I go back to Q1. When I see a B, I stay in Q2. In the R1 state, when I see a B, I stay in it. So here I stay in R1. But when I see an A, I go to R2. And in R2, when I see an R, I stay in R2. When I see an A, I stay in R2. When I see a B, I go back to R1. And my accept states are going to be Q sub 1 here, 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 or R sub 1 here, here, and here. Okay. Now, if you wanted to write the transition table in a function format, then you do delta with S and A goes to Q sub 1. Delta of S and B is R sub 1. Delta of Q sub 1 and A is Q sub 1. Delta of Q sub 1 and B as Q sub 2. Delta of Q sub 2 Q sub 2 and A as Q sub 1. Delta of Q sub 2 and B is Q sub 2. And then I'll also have to do the R's. So delta of R sub 1 and A is R sub 2. Delta of R sub 1 and B is R sub 1. Delta of R sub 2 and A is R sub 2. And delta of R sub 2 and B is R sub 1. Okay, so just the delta format took longer, and in the table tabular format, your transition function is a little bit more compact. Now let's go over a couple of examples to see what kind of languages, what kind of strings this machine accepts. So if we have, let's say that the input is A. So it started in S. When we see A, we go to Q sub 1, so we accept it. What if the input is AA? We start in S. With A, we go to Q sub 1. With another A, we stay in Q sub 1, so we accept it. What if it's an AB? We start in S, go to Q1. With B, we go to Q2, so AB is rejected, right? Now, what about ABA? ABA. We start in S. With A, we go to Q sub 1. With B, we go to Q sub 2. With A, we go back to Q sub 1, so we accept it. And, in fact, whenever we see an A, if we're in Q sub 1, we accept it. And if we see a B, and we keep seeing B, we go to Q sub 2, which rejects it. So you can see that this arc of the machine accepts strings that start and end with A, right? When you see an A, immediately you go to this state. So you accept A, and you accept if you see a number of A, which means that you start and end with A. And you also accept strings that start with A, keep going with some A, and then go with B and a bunch of B's, and then an A. So you just so this arch accepts all strings that start and end with A. If you look by symmetry, see, you go to string to state R sub 1 over B from S, right? So immediately, if your first element is B, you go into accepting strings with B, or strings that start with B and keep being B. And if they're interrupted with A, if they have the last symbol to be a B, they're going to go back to the accept state and they get accepted. So this arc of your machine accepts strings that are um, that start and end with B. Okay, so the language of M sub 4 is a set of strings such that A is a set of W if W starts and ends with the same symbol from A or B. Okay, so that is the state, that is the function of this finite automata here. Okay, so far we've designed a couple of finite automata, and they kept looking, or actually we analyzed and formally defined a couple of finite automata. We haven't actually designed any yet. Um, in and each of those finite automata that we've worked so far, they kept getting more and more interesting. And now we will formally define another quite interesting finite automata here, and we'll call this one M sub 5. So the state diagram for this finite automata is quite simple. In fact, it's only made of 3 states, and the initial state here is also an accept state. So we've got 3 states: Q sub 1, or rather let's call it Q sub 0, Q sub 1, and Q sub 2. And as I said, the initial state is Q sub 0, so we denote it with a arrow pointing to it. And then my alphabet is actually composed of 4 symbols here. So in Q sub 0, I stay in Q sub 0 if I encounter the symbol 0 or the symbol reset. And I call it re with the braces on each side of it. And that would represent like a reset. So if this machine was a machine that had the reset button, so reading the reset is going to be one of those symbols. So we stay in Q sub 0 if we see 0 or reset. If we see symbols 1, we go to Q sub 1. And if we see symbol 2, we go to Q sub 2. Okay. Now what happens if we are in Q sub 1? If we are in Q sub 1 and we see symbol 0, we don't do anything, we stay in Q sub 1. But we move back to state Q sub 0 if we see symbols 2 or the reset symbol. If we are in Q sub 1 and then we see a 1, we go to Q sub 2. And if we are in Q sub 2, if we see 1 or reset, we go back to Q sub 0. So if we see 1 or we see the reset symbol, we go back to Q sub 0. And if we are in Q sub 2 and we see a 2, then we go back to Q sub 1. And we stay in Q sub 2 if the input symbol is 0. Now, this has only 3 states, but because it has multiple symbols, multiple input symbols from its alphabet, the transition is a little bit more complicated. In fact, it has more arrows um, in the transition diagram. But every single state for every single symbol has an outgoing arrow. So Q sub 0, when it sees 0, it stays in Q sub 0. When it sees reset, it stays in Q sub 0. When it sees 1, it goes to Q sub 1. When it sees 2, it goes to Q sub 2. Q sub 0 stays in Q sub 0 for 0. For 1, it goes to Q sub 2. For 2 or reset, it goes back to Q sub 0. Q sub 2, for 0, it stays there. For 2, it goes back to Q1. And for 1 or reset, it goes back to Q sub 0. So the transition function here has more arrows because we have more symbols than states. Okay, so now we're going to formally define this function, and we treat the reset symbol as just one symbol. So this m sub 5 is going to be a 5 tuple q sigma delta q sub 0 and f. Okay, where q is made of 3 states, so it's a set of q sub 0, q sub 1, and q sub 2. The sigma in this example is actually a set of 4 symbols: a reset symbol, and symbols 0, 1, and 2. The delta is a function from q cross product sigma to q. We'll describe this next. And q sub 0, the initial state is q sub 0. Just happens that they have the same name. And the accept states is a set made of state q sub 0. Then again, I have to emphasize, this is a set and this is a state. Do not forget that, because that would make your definition incomplete. So now let's go and define our state diagram. So in this case now, the state diagram has also represented in tabular format. So it's going to be, so the delta is going to be over q cross sigma again, which will have 3 states: q sub 0, q sub 1, and q sub 2. And the symbols are going to be the reset symbol, the 0, the 1, and the symbol 2. So with the reset, we go back to q sub 0 wherever we are. So if we're q sub 0 and we see reset, we go to q sub 0. If we're in q sub 1 and we see reset, we go to q sub 0. And if we are in q sub 2 and we see a reset, we go to q sub 0. So reset effectively resets the system, goes back to q sub 0. As a byproduct of this, see, whenever the system, if the last symbol that you're reading is reset, then that sequence is going to be accepted. So it accepts automatically all the strings that end with the reset button. So if you're in q sub 0 and you see a 0, you stay in q sub 0. If you're in q sub 0 and you see a 1, you go to q sub 1. And if you see a 2, you go to q sub 2. See, q sub 0 with a 1 goes to q sub 1, with a 2 goes to q sub 2. Q sub 1 with a 0 stays in q sub 1. With a 1, it goes to q sub 2. And with a 2, it goes back to q sub 0. Q sub 2 with a 0 stays in q sub 2. With a 1, it goes to q sub 0. And with a 2, it goes to q sub 1. Now I'll give you 5 seconds to tell me what string is this language accepting. Or is this finite automaton accepting? Or in other words, what's the language of this finite automaton? So the 5 seconds starts now. 1, 2, 3, 4, 5. Okay, if you said that this machine accepts all the languages in which the sum of the symbols seen after the last reset is a multiple of 3, then email me, because I'm going to pass you and no questions asked. Well, not quite, but that is the language for this machine. Let's take a look at a couple of examples of this machine and the languages that it actually accepts. Apparently, if my string is actually a string W that has a bunch of stuff in it and the last element is reset, it's going to be accepted, because reset, no matter where I am, is going to take me back into state Q sub 0. So that's one of the strings that this machine accepts. Now, since we know that the last reset will take us back to state sub 0, all I need to know is to see if I'm in state sub 0, what does it take me to get back to state sub 0, Q sub 0, which is an accept state. So if after my last reset I have a 0, it's going to be accepted. If it is a 0 and then a 1, 1, and 1, so if it's a 0 and then a 1, 1, 1, it's going to be accepted, right? Or if it is a 1, 2, it's going to be accepted. 1 goes to Q sub 1, 2 goes back to Q sub 0. How about 2 and 1? Yes, that's going to be accepted too, because 2 goes to Q sub 2, 1 goes back to Q sub 1, right? How about 2, 1, 1, 1, 1, right? And this is after my last reset, right? After my last reset. If I had any. I could have a bunch of stuff before the last reset too, which would reset me anyway. So how about this one? Let's take a look at this one. Let's say that we have seen some reset or not. So we know that we start with Q sub 0. So with a 2, we go to Q sub 2. With a 1, we go back to Q sub 0. With a 1, we go to Q sub 1, we go to Q sub 2, we go to Q sub 0. So this takes me to Q sub 0. And if you look at all these elements, all these sequences that we have here, and if you play with a bunch of other sample strings here, you would notice that yes, in fact, this machine counts the numbers, or effectively adds the symbols together, and takes their modulo 3. And if that modulo 3 is 0, you will end up in a Q sub 0, and Q sub 0 is an accept state. So the language of this machine, M sub 5, is a set of all the strings such that the sum of all symbols, if I could spell symbols, in W after the last reset is a multiple of 3. This will be a little bit easier if we actually represent this function with its transitions in a functional format, or rather in a function format. So notice that the Q elements are Q sub 0, Q sub 1, and Q sub 2, right? So if you look at a delta of Q sub I and 0, it's going to be the same state, which is q sub I, right? So if you are in some q sub I and you see a 0, you stay in the same q sub I, right? How about the delta of q sub I and 1? Okay, let's take a look at q sub 0. Q sub 0 and 1 goes to q sub 1. Q sub 1 and 1 goes to q sub 2. Q sub 2 and 1 goes to q sub 0. So in fact, this goes to q sub I modulus, actually plus 1 mod 3. Because what happens if you q sub I, you add 1 to it, then you end up in q sub I plus 1, except if I plus 1 is 3, which mod of that will be 0, right? So q sub 2 over I goes to q sub 2 plus 1 mod 3. In fact, let me actually branch this out for you. So delta of q sub 0 and 1 is going to be q sub 1. Delta of q sub 1 and 1 is q sub 2. Delta of q sub 2 and 1 is actually q sub 3 mod 3, which is 0. Therefore, you end up at q sub 0. And this column represent that. What happens with delta of q sub I comma 2? That's the same thing. It's q sub I plus 2 mod 3. Let's actually branch this out also for you to so that you could see it. Delta of q sub 0 and 2 goes to q sub 2. Delta of q sub 1 and 2 goes to q sub 1 plus 2 mod 3, and I'm going to represent mod with the C++ notation for it, which is going to be q sub 0, and you see it here. And finally, delta of q sub 2 and 2 is going to be q sub 2 plus 2 mod 3, which is q sub 1. And there you are. So this is actually an interesting thing, an interesting machine. It is quite a sophisticated machine, you might say, and you would be correct saying that, which still you could represent it with a state machine. So as I talked to you when we started this unit earlier, I said that the finite state machines or finite automata are actually examples of computational devices with very limited amount of memory. In fact, this machine has only 3 bits of memory to be able to represent it. Actually, it could represent it with 2 bits, plus minus some bits for input symbols. But yet, it can recognize a sophisticated computational concept that is calculating if the sum of an infinite numbers of elements is a multiple of 3 or not. Notice that this machine, nothing in the language says that the string could be should have any bound on it. It could have any number of symbols. If it is an infinite symbol, you would have to wait indefinitely for the machine to recognize it, because it has to see the last element in the sequence. But aside from that, the machine has quite sophisticated or rather functionality, and that is calculating whether or not something is multiple of 3 or not. Now, as an example for you to work at home, I would like you to write the description of a finite state machine. So this is basically I don't want to call it homework. Try it yourself. So I would like you to write the description of a machine, and we call this an M sub 5, M sub 6 actually, which recognizes a language so this is a finite automaton whose language is set A of all strings such that sum of all symbols in W is a multiple of I for some natural number. Okay, so I would like you to try to formally define this machine, the machine M sub 6, to be a finite automaton whose language is a set of all strings such that the sum of all the elements in the string are a multiple of I for some I integer. In this case, we showed you a I being 3, and of course to simplify this I took this reset symbol out, so you don't have to worry about the reset symbol. And think about it, and we'll start our next unit with explaining this automaton M sub 6 and writing the definition for it. Hint here, let me just give you a hint, and that is, so hint, use the mathematical equations for delta of Q sub j and K. K is going to be from the set 0, 1, 2, all the way to I minus 1. Okay, so that's that. So we talked about finite automata. We formally defined them. We went through a couple of examples to see how from a state machine you could define formally your automaton or 5-tuple, and we talked about what is the language of a finite automaton, and from there we went through 5 examples, and we saw from the formal definition what languages these automata accepted, and we ended up with a very sophisticated finite automaton actually in this very last example. And I gave you a simple work it out yourself kind of thing to define formally a finite automaton M sub 6 such that that machine accepts the language of all strings in which the sum of elements are equal to a multiple of some natural number. And this is going to be where you would see how an actual formal definition comes in handy when, for a machine like this, you cannot really use a state diagram to show how it works, because I is some natural number, which means that we don't know how many states it has. I mean, it may have up to I minus 1 states, or actually up to I states. And so we don't want to bog ourselves down with an informal definition, which is easy to and intuitive to grasp, but it's really hard to actually draw when the computation, or rather the descriptions of our machine are boundless, as we see here. So with this, I would draw the unit 2 to a conclusion, which was about finite automaton. And in the next unit, we will formally define the definition, the computation. We would formally define what it means to compute, and using a finite automaton, of course. And then we see how we can design finite automata um, with the concept of reader as automaton, and then we explain about regular operations on languages and prove some certain properties of regular expressions, regular operations, such as closures under union, under um, intersection, and complementation. And then we'll see what the limits that we hit with deterministic finite automaton to mathematically prove other closures of our regular operations, which warrants looking into and building another sophisticated machinery, mathematical machinery, for us to be able to prove those closure properties, and that would be non-determinism. So with this, I hope that you enjoyed this unit, and as always, please participate in your discussion boards. If you have any questions, feel free to stop by my office or go on the online office hours that are posted on the blackboard, or in general, just email me if you have any questions. I hope that this was a fluid and an easy lecture so far, and we'll talk to you in the next unit.